Hey everyone, and welcome. Today we're going to jump into a really cool puzzle, something that's right at the heart of how our data systems work. It's a story about a superstar tool, a tool that's absolutely amazing in one place, but just completely faceplants in another.
So that brings us to the big question for today. How can a data structure that's just brilliant in memory, absolutely perfect, suddenly become a total disaster when you have to put it on a disk? It doesn't really make sense, right? Well, that's exactly the mystery we're going to solve.
Okay, so to really get why it fails, we first have to meet our hero. Let's talk about the data structure that is, for all intents and purposes, the perfect tool for its job, as long as that job is organizing data inside your computer's memory.
And that hero is the binary search tree, or BST for short. Now, the magic of the BST is how simple and elegant it is. See, every piece of data is a node. Each node has a key, and then it just points to two other nodes. One for anything smaller than it, and one for anything larger. That's it. That one simple rule means the whole thing stays perfectly sorted, all the time.
And in its natural habitat, inside your computer's RAM, the BST is an absolute speed demon. Finding stuff is incredibly fast, because with every single jump you make, you get to throw away half of the remaining data. It's like playing a guess the number game on steroids. That's what we call logarithmic time, and it is just crazy efficient for in-memory lookups. But what happens when the data gets too big for RAM? What happens when our elegant little BST has to move out of its comfy home and live on a hard disk? Well, this is where the story gets ugly.
And here's the heart of the problem. You got to understand, RAM and disk are two completely different worlds. Accessing RAM is pure electronics. It happens in nanoseconds. We're talking billions of a second. But accessing a disk, that's a physical thing. A little arm has to literally move across a spinning platter. That takes milliseconds, thousands of a second. Now, nano versus milli might not sound like a big deal, but it's a difference of 1,000,000 times. It's like comparing a race car to a snail.
And it gets worse. Disks don't read tiny little bytes one at a time. Nope. When you ask for one little piece of data, the disk goes and grabs a whole chunk, what we call a page or a block. So get this. Every single trip to the disk is incredibly expensive, and you're forced to read a ton of data even if you only needed one tiny part of it. Remember that. It's super important.
Okay, so keeping all that in mind, the massive speed difference and the block-based reading, let's look at the 3 fatal flaws that make our BST just fall to pieces on disk.
All right, problem number 1 is something called low fanout. Fanout is just a fancy word for how many children each node in the tree can have. And for our BST, that number is always 2. Just 2.
So why is that a problem? Well, because each node only has 2 branches, the tree has no choice but to grow down. It becomes tall and skinny like a skyscraper. Now, if you need to find something way down at the bottom, you have to make a whole bunch of jumps to get there. In RAM, those jumps are basically instant, but on a disk, oh man, every single jump from one node to the next means another agonizingly slow disk seek. A tall tree means lots of jumps, which means lots of disk seeks, and your performance just dies.
Problem number 2 is a little more subtle, but it's just as bad. It's called poor locality, and this is all about where the different nodes are physically stored on the actual disk. Just think about it. When you're adding new nodes, they just get stuck wherever there's room. On a disk, that means a parent and its child could be on completely different sides of the platter. So when your code follows a pointer from a parent to its child, you're not just making a neat little jump in logic, you're forcing that physical read head on the disk to fly from one spot to a totally random one somewhere else. That kind of random jumping around, it is, without a doubt, the slowest possible thing you can ask a disk to do.
And that brings us to the final nail in the coffin. Problem number 3. You see, even the thing that's supposed to keep a BST fast, the process of balancing it, turns into a total nightmare on disk. See, if you're not careful, a BST can get really lopsided and its performance just tanks. To fix this, the tree has to rebalance itself using these little moves called rotations, just shuffling pointers around to keep the tree nice and bushy instead of tall and stringy. In RAM, this is nothing. It's super fast. But on disk, every one of those little pointer changes is a tiny random write, and we've already established that random access is public enemy number 1. So the very thing you're doing to help performance is actually killing it.
So there you have it. Our hero, the BST, has failed. But from its ashes, we can figure out a totally new blueprint, A new set of rules for building a data structure that's designed specifically for the disk, right from the start. And that blueprint has one golden rule, one guiding principle above all else: minimize disk access, period. Every single design decision we make has to serve that one purpose. We have to avoid going to that slow, clunky disk as much as humanly possible. So, how do we do that? Well, it's simple. We take the BST's biggest weaknesses and we turn them into our strengths. Instead of a tiny fanout of 2, what if we designed nodes that could hold hundreds, maybe even thousands of keys? That gives us a massive fanout. And what's the result of a massive fanout? You get a tree that's short and wide, not tall and skinny.
And that is the magic right there. By cramming hundreds of keys into one single node, a node that, hey, conveniently fits inside one of those disk pages we have to read anyway, we can cover a massive amount of ground with every jump. A wide, shallow tree means you can get from the top to any leaf in maybe just a few hops, and a few hops means a few disk seeks. We've just solved the problem.
So this new blueprint, the one born from the failures of the BST, it leads us to a totally different kind of tree structure. So what do you call a structure that's wide, that's shallow, and that's built from the ground up to dominate on disk? Well, it's called a B tree, and it is the absolute foundation of pretty much every modern database system out there. But how that works?